Okay, so very happy to have an anchor in this thing. Pravesh, is there there's an anchor on the page.
Yes.
Okay, Pravesh Kothari from Princeton University. Tell us about tensor stuff.
Yeah, I don't need to wear a microphone, right? Yeah, okay, good. Yeah. It's actually pretty good to be mistaken for Ankur Moitra. So if you continue to think of me as Ankur Moitra, please do. Right, yeah, so I'm going to talk about this work on overcomplete tensor decomposition. And if you haven't seen the word Koszul Young Flattening before, it might look mysterious, hard, whatever, but it's not. I'll define it very concretely. It's a very simple operation on tensors that I'll concretely describe. Yeah, and this is joint work with Ankur Moitra and Alex Wein, two amazing co-authors that I've talked to about tensor decomposition, over the years. And I think I've learned a lot from them. And, this is maybe the only paper we were able to write together. But I think I've been talking to these people about tensor decomposition for years now. So I'm glad I have something to say together with them. Okay, so here's the question I'm going to be interested in. A tensor for me would be an object of the following type. Okay. So when I write a to the bracket I mean like I have a sequence of vectors, and the ith vector in the sequence is a to the I. Okay. And I'm going to think of tensors in n1 cross n2 cross n3 dimensions. What that means is that these vectors ai, bi, ci are in r to the n1, r to the n2, and r to the n3 respectively. Okay? Good. If you come from like algebraic geometry, you are probably used to a more abstract notion of a tensor, and this is maybe a particular representation of it. But for the purpose of this talk, this is the definition of a tensor for me. Okay? Good. Okay, so I'm going to call a tensor rank 1 if, there are vectors A, B, C such that the tensor equals A, tensor B, tensor C. By the way, this notation simply means that, to describe an entry of this object, I have three indices, I, J, K, and then the I, J, K entry is simply the product of AI, Bj, and Ck. Okay, that's what this notation means. Cool. All right, maybe I'll write one more definition here and then proceed. So definition. So I'm going to call n1 by n2 by n3 tensor a rank little r tensor for a positive integer r if r is the minimum positive integer, such that T can be written as a sum of r rank 1 tensors. As a sum, okay. R rank 1 tensors. Okay. So yeah, I got a bit tiny at this point, but hopefully you can follow. Good. Okay, so I'm going to be interested.
Maybe it's worthwhile saying that for two-dimensional those matrices, it's the same definition of right?
Yes, yeah, I'm actually coming exactly to that point. Good. Yes. So let me write down a algorithmic problem, and then I'll make a connection to matrix time decomposition that we're all familiar with, and make the point that Abhi just made. Okay. So the algorithmic problem that I'm going to care about today is you're given a n1 by n2 by n3 tensor T, meaning you're given basically this, a value for each possible triple ijk. And your goal is to basically find a rank decomposition. So I'm going to write the here and then you should be suspicious of what I'm asking for, but I'll come back and explain what I mean, okay? Okay, so when I say this, find the rank 1 components in okay, so in some sense, this the should bother you because, who knows, there may be multiple, rank 1 decomposition of the same rank or even the minimum rank. But, I'll come back and talk about when this question is interesting and why we care about it, etc. But let's go back to, Avi's comment from earlier. Imagine the case when N3 is 1. Okay? Then, effectively speaking, this is a matrix. It's an N1 by N2 object. And you can see that, I'm simply asking for a rank decomposition of this matrix, right? And notice that, this definition of rank agrees with any other definition of rank you might have seen, right? Like in algebra, undergraduate in algebra, we see several equivalent definitions of rank. This one is probably one of which you've seen. If not, it is equivalent, okay? Not too hard to show. Now, this question is basically not that meaningful for the matrix case, right? And the reason is this so-called rotation problem. It's a problem because, in the world, where this question is interesting, we would like rank 1 decompositions to be unique, and I'll come to that in a second. But from that perspective, not having a unique rank 1 decomposition is a problem. And in the context of matrices, one generic reason for why this holds is the so-called rotation problem. And I mean something simple, that if M has some rank 1 decomposition like this, then I can just multiply on both sides by a rotation matrix and its inverse. And I have the same matrix, but the rank 1 components have changed, right? And so this basically holds for every matrix in the world. So in that sense, rank 1 decompositions are very non-unique because they rotating all of the vectors that arrive in it by the same matrix would produce a new rank 1 decomposition. Does that make sense?
Would that also rotate M?
I'm gonna apply U and U inverse. Let's say it's square. So it won't, right?
No, I think can't you just apply UU transpose in the middle between AI and BI, right?
Sorry, yeah, that's okay. You're right. Yes, that's what I should do. My bad. Yes. Yes. Yeah, correct. Sorry. That's not equivalent to what I was writing. And this gives you a different rank 1 decomposition. And so, that shows that in some generic way, matrix rank decompositions cannot possibly be unique. Okay? But it turns out that tensor rank decompositions are generically unique. Okay? So let me state a result, basically just a fact for now. And then, I'll tell you a little bit about why we care about it. Okay? So,
Actually, something is still bothering me.
yeah.
You look at that decomposition, every element in the sum doesn't change when you change.
Put parentheses, it will be clear.
No, still.
No, they do.
Still, if you do the product,
Yeah,
it stays the same, right?
The same rank 1 matrix with different
I
values.
agree with that.
Same rank 1 component.
Uh,
Different vectors, but
You're right.
Yeah.
yeah, that's correct.
Yeah, I think you want the vector, so.
anyway, okay.
Yeah.
But you have problem when you have multiplicity of eigenvalues.
That's another, yeah. So
Not generic.
that's less generic. Yeah, exactly. So I wanted to say this because it's, this is a generic problem, right? Like even if the vectors are random or whatever, this would continue to affect you. The multiplicity problem is of course also an issue, but generically it won't arise. Like, if I have a square matrix, let's say even a symmetric matrix, the eigenvalues will be distinct with probably 1 in any reasonable model. Yeah, so that's I actually care about recovering the vectors for this purpose. I'll come to explaining why this matters now, okay? So unlike the matrix case, tensor rank decompositions are unique. I'll say generically unique for R less equals Cn square for some constant C in interval 0, 1. Okay, so basically you can have n by, so yeah, for the purpose of this statement, I'm talking about n by n tensors, less notation. So if you take a n by n tensor and you form it by choosing vectors ai, bi, ci, generically, let's say you choose Cn square of this, triples of vectors, use each triple as a rank 1 component, add them up, this gives you a tensor. And such a tensor does not have any other decomposition of rank R.
So I can't see, C is in 0, 1 or?
Yeah, C, yeah, sorry, yes. C is in the open interval 0, 1. As in, like, it's certainly less than 1. Probably, yeah, I don't know exactly what is known here. Do you know the?
I think it's third is enough.
Okay, third, yes. Yeah, so it's a concrete constant. I didn't look it up before, but so I'm sure this is known classically, but one reference for this, in case you wanna look up, is Bacci, Chiantini, and Ottaviani. It's not a super difficult theorem. It kind of confirms something what you might expect, okay? Let me tell you why n square is obvious, by the way, or n square is like a reasonable bound, okay? One way you can decompose a tensor is by just going to, like, thinking of it as n slices of n by n matrices. Then for each n by n matrix, basically doing a rank decomposition. So you get like n components. And then, like, just piecing them all together, okay? This gives you generically a decomposition with about n square components. Right? What this is saying is that, so, once you get to a point where this algorithm gives you a decomposition, clearly things will not be unique. Right? Because it comes from matrix rank decompositions, and we already saw they are not unique. What this statement says is that if you are a constant factor below the number of components guaranteed by this trivial algorithm, then in fact, as long as the components are generic, the decomposition would be unique. Okay, so you can see in that sense, it is almost the best possible thing you could hope for. Okay, good. So the question we are going to be interested in is, are there polynomial time algorithms for this decomposition question? Okay, and before telling you more about this, I want to talk about why you might care. Yeah, maybe I'll say here so that I can use the big board for more interesting things. So I won't, talk too much about applications. You can ask me later on if you care about any of these. But one very important reason you might care in algorithm design about tensor decomposition is that many questions in statistical estimation can be reduced to the problem of decomposing, tensors, usually of order 3 or larger. So what I wrote over there is an order 3 tensor because, it has like 3 modes or 3 indices. And so it turns out that many questions in statistical estimation can be reduced to questions about decomposing order 3 tensors or beyond. Okay, so there are many examples like this, but mixtures of spherical Gaussians, for example, is a canonical example. I want to explain, this in writing or in detail for the purpose of this talk, but basically, if you're given samples from k Gaussian distributions, like, you just like take them, let's say equal number of samples from each Gaussian with distinct but unknown means, and all covariances, let's say identity. And your goal is to somehow decide what the means are. And you only see like the samples taken together. So, this is the question of, let's say, this is maybe one instance of the question of learning mixtures of spherical Gaussians, where the goal is to basically learn the means. And one strategy that works here, and I'm going to describe the strategy in like, a line. This strategy I'm going to describe in the context of spherical Gaussian, but it makes sense in many, many other problems, is to compute the moment tensors of the input samples, or compute the empirical moments, right? So for example, if you're given samples x1 up to so on, then you can compute, let's say, you can compute the empirical moment tensor. So right, basically take the tensor, take its outer product with itself 3 times and add them up. This gives you like an n by n object, okay? And now what you can show is that if you look at what this tensor is, sometimes after some cleanup, sometimes kind of obviously, there is a decomposition for this tensor, a low rank decomposition with this tensor, that basically relies on the unknown parameters you're looking for. So in the context of mixtures of Gaussians, you can show that the components are basically the means, the unknown means. So if you could somehow decompose this tensor, which you can, generate from samples quite efficiently, you would solve the task of determining the means of a mixture of unknown k Gaussians. Okay, so this, for example, is a strategy invented by Daniel Xu and Shyam Kakade in 2011. But like I said, there are many, many examples of this. I'm just quoting one. In estimation problems, there are many such applications. Almost all of them basically come from like some version of the method of moments, right? Like you compute moments of samples from some distribution, show that these moments encode information about the parameters that you care about in terms of the low rank decomposition. And if you're a decomposition algorithm, then you would be able to recover the unknown parameters. So that's one reason, you might care about it. I want to talk about, okay, maybe I'll come to another reason in a bit when I state some results. So at least you see that there is some reason to care about this, right? These decompositions are unique generically and there is some reason to care about it. So let me tell you what is known about this problem, okay? So it would be great if tensor rank decompositions had a polynomial time algorithm, but we are not so lucky. In some sense, for matrix rank decompositions, we get super lucky that there is a very nice polynomial time algorithm. Such an algorithm is unlikely to exist unless P equals NP for tensor rank. So, we know that tensor rank is NP complete. Let me say NP hard, think of it as a search problem. So tensor rank is a problem of given an n by n tensor, tell me its rank. Okay, so compute the rank of it. A min rank decomposition, of course, requires that you first be able to compute this. Any algorithm to compute min rank decomposition has to also certify that the rank of the tensor is whatever you're claiming it is. So the NP hardness of tensor rank shows that you can't hope to do this, for every possible input tensor, right? Unless.
What's the best hardness of approximation?
Yeah, I looked it up just before coming here. It seems to be 1 plus some constant. So,
the rank.
Yeah.
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 I mean, presumably it should be much, much better, but this is the best we've got. Yeah. I didn't search too hard. I just looked at like one recent paper that claims some constant of 1 plus 1 over 1800 or something. So that's, yeah. I think it is probably just extracted from the NP completeness results, just like look at what hardness approximation they yield. So I don't think people have really optimized it. Yeah. Yeah, but basically, yeah, that's maybe the first negative news. But it turns out that, despite this hardness result, we can do a lot. Okay. And so despite the fact that tensor rank is NP hard, when the components are generic, which in some sense is a situation we care the most about, because then, the rank decompositions are unique, and therefore, the components have some meaning. So maybe presumably, at least in these applications, this is the situation you would care most about decomposing. And it turns out that there we do get lucky. There we do have interesting algorithms. Yes.
Do we have a definition of generic?
Yes. Okay. Yeah. Good question. For me, for the purpose of this talk, so it's generic in the standard sense of I guess algebraic geometry, but I'll give a concrete definition. For any algorithm look at the tensors that it succeeds in decomposing. If the failure set can be described by zeros of a non-trivial polynomial in the components, then I'm going to call that generic. Because, if it's a finite degree polynomial and I only fail on the zeros of it, then there's a measure zero set that I fail on and everything else is succeed on.
Failures meaning the entries where you disagree with the decomposition?
Yeah, let's say, right? Like, you can think of it as even a decision problem. So think of tensor rank and think of, the tensors, the input components of the tensor at which the algorithm correctly decides the rank, and think of like where it incorrectly decides the rank. If the set of components where the algorithm fails to decide the rank correctly, form the zero set of some non-trivial polynomial. So a polynomial that should not be identically zero. Then, I'm going to call it, generically successful algorithm.
Okay.
Okay, so
You have all possible inputs of size
Yes.
n1, n2, n3.
yes.
And you have a polynomial in that.
Yeah, and my polynomial is in the variables that stand for all possible entries of all possible vectors in the decompositions.
Yeah.
And the algorithm should fail only when these numbers satisfy some polynomial equation, and the polynomial should be non-trivial. That's it. Yeah. This sounds like unnecessarily abstract. Most of the times, the algorithm that we're going to look at would be like a bunch of different matrices should be non-singular. So, these polynomials are basically some determinants of some appropriately constructed matrices. So they're not that complicated, right? So, but anyway, like that's the definition. So in particular, success generically would mean that, there is basically only a measure zero set of input components on which my algorithm will fail.
So in particular, the NP hardness is always going to be in some measure zero.
Well, I haven't told you the results, but yes, that's where we're going. Yes. Like the parameters, presumably you can prove NP hardness beyond the parameters I'm looking at today, and then it is quite possible that you can prove NP hardness in the regime where the generic decomposition algorithms don't succeed. But yes, right now I guess there is that possibility. Okay, so I won't write down this verbosity of definition for what it means to be a generic component tensor. I hope you got it. If you don't, ask me. I'm just going to use the word as is now. So for generic components,
But maybe it's worth saying that tensor rank is not defined by zeros of polynomials, unlike rank of
Correct.
matrices.
yes. Otherwise, we would have been.
Otherwise,
Otherwise, it would have been trivial.
Yeah.
So amongst the many facts about matrices that don't seem to generalize to tensors, we don't have an analog of characteristic polynomial or determinant and things like that. And so we can't encode the rank in terms of non-zeroness or non-triviality of some polynomial. It would have been great, and then this talk would have been trivial, but this talk has something interesting.
There is a recent research showing that asymptotic rank is defined by polynomials. Yeah, Princeton and Wein. Yeah, I mean, you don't want to go to asymptotic rank.
Yes.
But there's a natural analog which is characterized by polynomials.
Okay.
Which something should have been known decades ago, but was just discovered.
Yeah. Okay. Cool. Yes. I'm going to look up what asymptotic rank is after the talk. Okay. So actually, now that I defined generic components, I want to give you two more, models of components to keep in mind. And you should think of genericity as, in some sense, the least possible, restrictive assumption on the components I'll make today. And I want to give you the two other things because it's going to be interesting when I ask you some open questions towards the end. So I'm going to talk about smoothed components. So smoothed components means that I start with a tensor with arbitrary components, but that's not your input. I'm going to look at every vector AI, BI, and CI, and then add an independent, let's say Gaussian vector, small Gaussian vector, to each of the vectors. I'm going to call this smoothing of a vector. I'm just basically randomly perturbing each possible component. Okay. You can think, clearly such smooth components would satisfy genericity assumptions, right? Because I'm going to be off the zero set of any fixed polynomial. So of course, smoothing implies genericity, but the other way around need not be true, right? Like this is a specific model. This is like, more general. And, I'm also going to talk briefly, at least in terms of comparison, to tensors with random components. And here it means that, the vectors AI, BI, CI are chosen as independent, let's say, standard Gaussian random vectors. Okay, so this is in some sense the most restrictive model. This is the least restrictive model. This is somewhere in between. Okay. Okay, good. So let me tell you what we know about, algorithms for this problem. So all the algorithmic results I'm going to talk about right now hold for generic component tensors. Okay. It's only towards the end of the talk that I'll come back and compare them with these two other models and tell you what's interesting about them. Okay, so there is an algorithm which kind of weirdly is called Jennrich's algorithm or Jennrich's algorithm, even though it appears in a paper of Harshman. And we call it Jennrich's algorithm because Harshman credits Robert Jennrich for coming up with ideas in it. Although people have tried to backtrack this reference, and turns out that Jennrich did not quite invent the kind of algorithm that we call today Jennrich's algorithm, but the name has stuck. Okay, so really maybe the credit should be to Harshman. And this algorithm, it's a very nice algorithm. It reduces tensor decomposition to simultaneous matrix diagonalization. So it's a very cool algorithm. If you haven't seen it, you should go look it up. I'm not going to tell you the details of it, but I'm just going to give you like maybe a 2-line version so that you can see how simple it is. Okay. So you start with this input tensor, which is an n by n by n tensor. And I'm going to construct a matrix out of it. And this matrix is going to be obtained by doing what is called a random contraction. Okay. So what I'm going to do is I'm going to compute a matrix whose ijth entry equals the inner product of the last mode of the tensor, the kth mode of the tensor, with a Gaussian vector. Okay, so think of GKs as independent standard Gaussians. I'm going to call it contraction because I'm kind of, adding up or averaging out the last mode of the tensor to produce a matrix by this operation.
A random linear combination of the slices.
A random linear combination, yeah. Here is a different way to think about it. If you think of the tensor as, n3 different slices, then, you're just multiplying each slice by a scalar, a random Gaussian, and then adding them up. Right? This is, a contraction of all the slices into one slice. So this is the matrix, and you can decompose it. But, we already learned that, that may not by itself be enough. It turns out that if you do it twice with independent Gaussians, so G and G prime, then it turns out that there is exactly one, with probably one, there is a unique simultaneous rank 1 decomposition for the two matrices so produced. And there is a very natural reduction of the simultaneous diagonalization problem to eigenvalue decomposition. So you can solve it efficiently. Okay, so if you haven't seen this, I've been teaching this for a few years. I have lecture notes on my webpage. You can take a look. It's a very nice algorithm. It works as long as the rank is at most, so for the square case n, right? And in general, like, R at most, and like the minimum of n1, n2, n3 suffices, right? And you can see why I would need that. Like, think about just the square case, so n by n tensor. Then, I'm going to convert it to a matrix. For me having even a chance of a simultaneous decomposition in the same vectors, the rank, the rank of this matrix better be less than n. Right? Otherwise, I'll certainly have multiple decompositions. Okay, so basically, like, R less equals n is this, in some sense, benchmark guarantee. It's due to Jennrich or Jennrich's algorithm. And our focus today would be on the overcomplete case, because this is like the standard classical algorithm. We're gonna say, oh, a tensor is overcomplete if R for the n by n case is bigger than n. Okay, so let me tell you what we know about the overcomplete case. This is in some sense where all the action is, so to speak.
Why complete? Why overcomplete?
Yeah, good
Sorry.
question.
All the questions, yeah, okay.
Yeah, I don't know, but I would ask Avi.
No, I don't like it, but it's historical reason.
Huh. Yeah, I don't know. Yeah,
Maybe it's due to Jennrich.
No, no.
yeah, yeah. I don't know. Yeah,
Yeah.
yeah. I mean, for us, it only matters that n is a natural threshold of, it's a threshold of a natural algorithm. And, that's our benchmark. We would like to beat it. And whatever beats it is overcomplete for us, right? I don't have a great reason for this terminology. Okay, good. So, okay, so I'm going to tell you maybe 3 results. There are lots of results here, so I'll just focus on 3 because those are most relevant, and then I'll tell you what we do. Okay. So, in some sense, the earliest result for the overcomplete case, earliest interesting result is due to Koszul. I think maybe 77, and he gives an explicit condition on the components, which first you can check that generic vectors will satisfy with always satisfy. So it's like some kind of polynomials being non-zero or whatever. It can be encoded as non-zeroness of some polynomials. So it's a nice condition, and it can succeed in principle up to rank 3n/2 for the n by n case. Okay. Now, I say it can succeed up to that rank because we don't know how to check this condition efficiently, even given the components. And, even leaving that aside, we certainly don't know any algorithmic ways to exploit this condition. So such results are called uniqueness results in, this context of tensor decomposition. They do identify explicit conditions, encoded as, let's say, non-zeroness of polynomials or whatever, that imply overcomplete tensor decompositions being unique, even if they don't somehow, lead to algorithms. Okay. The algorithmic results, unfortunately, are maybe fortunately, are much more recent. So, I'm going to start at 22, but you'll see exactly where we start here. So if R is n plus L for some parameter L, then, the result gives an algorithm that runs in time basically exponential in L. And of course, polynomial in length. So, you can do, for example, n plus log n rank tensors in polynomial time, but not far beyond. Okay?
Generic.
Generic. Yeah, everything I'm saying applies to only generic.
The uniqueness is guaranteed up to n square, right?
Yeah.
Yes, but that's not, so Koszul is identifying an explicit, condition, and I'm calling it explicit because he's saying that the following polynomial should be non-zero. Okay. Generically, so this, this kind of a proof, for example, is not via an explicit condition. So there is kind of a qualitative difference between the two kinds of results. Yes. So algorithmically though, this Chen Rademacher, 4-ish years ago, they showed that you can go to, let's say, n plus log n in polynomial time. And then, very excitingly, /maybe like a year and a half ago, Pascal Poiran found an algorithm that succeeds up to 4n/3 generic components. Sorry, what?
That less than 3 hours?
Yes. So yeah, this is not algorithmic. Yeah, so yeah, we haven't crossed Koszul yet. But next slide. But yes, a few months after, we were able to give an algorithm that succeeds up to for the square case, for this n by n case, all the way up to 2 minus epsilon n for any fixed epsilon. So basically, the running time scales exponentially in this 1 over epsilon. So you can go to, let's say, 2 minus 1 in log n, but not beyond. Okay, so that's the result I want to tell you about today. Good. Yeah, maybe. So after this point, what I'm going to do is like tell you like a key component, and then give you a little bit of a background on like this theory of arithmetic circuit lower bounds or whatever where it comes from. I won't tell you any big details there, but at least some references. But is there any questions so far up to yeah?
Is 2n the maximum possible rank of an n by n by n?
Yeah, this is an amazing question, and I am going to come to it in the next part of the talk. So you can see that we are fighting for constants in front of n. We know that certain kind of techniques, of which what I'm going to do today is an example, cannot beat 6 times n, and this is a paper co-authored by Avi, like 7-8 years ago. Yeah. I guess the paper said 8n, but you can refine the analysis to 6n.
We also say 6n.
Oh, okay, 6n. Okay.
With this not coming off and with
Okay. Okay, so it is so 6n is like a lower bound on the kind of tricks I'm going to use today.
So what is the maximum rank for the tensor that's n by n by n?
So it can be omega of n square. So this is
n squared over 3.
Is it n squared over 3? Okay, yeah. So n squared over 3.
N to the d minus 1 over d.
Okay. Okay, good. Yeah, so it can be omega of n squared, but we are haggling for constants in front of n because it turns out that this is a hard problem and has some non-trivial connections with proving arithmetic circuit lower bounds. That's some excuse that we give to show why we are failing in some sense. Well, less glibly, I think, it does show that there is some, there is something new that you've got to do to go beyond constant times n. And perhaps that's out of the range of current techniques. Yes?
Could you compare these results with the current best, like explicit tensor rank lower bounds?
Good. I don't know what the state of the art there is actually. Sorry.
It says it's 2n.
Is it 2n? Do we know?
Yeah.
Okay. Yeah. So 2n does seem to be like the natural limit of many different tricks. It turns out that in fact Koiran also in his paper, so he reduces this problem to a natural question called commuting extensions. And it turns out that the question stops making sense at 2n. So he was able to get an algorithm till 4n over 3, but there was a natural barrier even for his trick at 2n. It turns out that with our, like this more elementary way of looking at things, you can actually get even his method to work till 2n. But all these methods seem to fail at 2n, and perhaps this arithmetic circuit lower bound is also failing at 2n, so maybe it seems kind of related. But I don't understand these things very well, so I don't want to say anything more than that. Yeah.
More interest in this was from the arithmetic circuit lower bound, or from the application?
Yeah, so all my previous work is on decomposing tensors with like smooth components or random components. But it turns out, so maybe I'll launch into discussion right now, given that we're already doing it. So it turns out that, so maybe I'll define a key object and then tell you, how it relates to algorithms. So this is an object that arises quite naturally in proving lower bounds. I'm going to call it rank detector in today's talk. So basically, the philosophy of this definition is that the only thing we know how to do is to compute matrix ranks. And so we want to formalize a definition that captures what's the best we can do by reducing tensor rank to matrix rank. Okay? So, you want to compute some map that takes a tensor and computes a matrix out of it.
So linear. Or you not.
Well, ours is going to be linear, but, for the purpose of the definition, it could be more general, right? Your lower bounds.
Because the work is defined linearly, you have to be,
Well, okay, let me write down the definition. Yeah, I'll say why it makes sense to have even nonlinear objects. So let's say, I transform a tensor to a matrix with the property that there is some f such that some function, like, this f is given to you. F of rank of m of t is always the lower bound on rank of t. This has to be true for every tensor. Okay. And moreover, so maybe I'll just say, this should hold with equality if T has generic components. Okay? If I give you this particular way of transforming a tensor into a matrix along with this function f, then notice that it certifies, because of this correctness property 1 here, it certifies that the rank of T is whatever it is.
Are we thinking random, like in the Jennrich's algorithm, or?
You mean like the map itself?
Yeah.
No.
So it has to hold here for, like, this has to hold here for every tensor simultaneously.
I see.
It has to be a clever.
Sorry, what?
It has to be a clever man.
Yes. Yeah, but it turns out that there is a closely related map to Jennrich's algorithm that does work. So it turns out Jennrich's algorithm can be seen as like an application, as a special case of this so-called shifted partial derivative method in lower bounds. So it's not so surprising that that thing works. There is a deep connection between whatever works there and these kind of rank detector gadgets, at least whatever works for generic components. And you can see, yeah.
I think a really good example is just flattening.
Yes, I was going to give an example. Yes. No, it's great. Yeah. This is, it's nice that I was predicting what I'm going to do next. Yeah. So, good. Yeah. So first of all, notice that, such rank detector gadgets would arise naturally in any attempt at constructing an explicit tensor with a large rank, right? Like, you'd have to somehow certify that its rank is large. And what would you do to do that? Well, you'd give me a certificate, and I just encode it basically these definitions encode that f of this map M is a certificate of rank, right? So yeah.
So because your algorithm only cares about generic tensors, why do you need condition 1?
Condition 1 is what allows me to get a certificate that rank of T is what this map tells me. Like, remember what I'm doing at the end. So you are given an explicit tensor T, right? Genericity is not a property I'm going to check.
Yes.
Right?
Yeah.
So you just have a tensor at the end. You apply this map, right? And you get an estimate of the rank. Now, I would like to claim that this is indeed the rank of the tensor.
Oh, I see. So you actually need to certify that your algorithm works.
Correct.
But
yes,
if I don't care about that thing.
Very, very good question. Hold on, because I want to talk about that. It turns out that if you don't insist on certifying, then you can likely get better results, and that's going to be one of the open questions I will ask.
Okay.
Yes, but you're right. Like, here we are looking to certify the rank, right? So you're absolutely right in noticing that this, in principle, is not required to succeed in decomposition. But in any case, it is definitely what you encounter when you're trying to construct explicit tensors of high rank. And so it turns out that, you can often take these methods that arise in constructing explicit large rank tensors and design algorithms for decomposing or at least rank detection with some gadget that arises naturally in the argument. Okay? So this connection way is what made precise in a very nice paper of Kirk, et al. And Saha, I think 4 years ago. This connection between decomposition algorithms and these kind of, certificates or gadgets. So they did it in the context of this polynomial decomposition problem. I won't tell you more about it, but it's like a generalization or closely related problem to tensor decomposition. But basically, like in the context of doing this, they observed that Jennrich, for example, can be thought of as an instantiation of the method of shifted partial derivatives, among other things. Okay, so what we are going to do today is take another rank detector gadget that actually arose in the context of proving lower bounds on certain tensors. In fact, if you know what that is, the matrix multiplication tensor, which basically amounts to proving lower bounds on a number of arithmetic operations required to multiply to n by n matrices. Okay, so it turns out there is a way to encode this question as a tensor rank question. In fact, that's the main origin of interest in complexity theory for n by n tensors and their rank. So this Koszul Young Flattenings is going to be one such gadget that arose in a lower bound proof. In fact, the best known lower bound that we have for matrix multiplication tensor comes from these particular gadgets, and that's what we're going to use today. So our method, or like our result, is in some sense like an application of the same philosophy as in Gerd-Kayal-Sahab. Okay, so I'll come back to that. But before you see interesting flattenings, let's see some uninteresting flattenings, some things that you might think are natural. Okay, so let's take two examples. Here's one example. You can just forget about so I have n3 different slices. You can forget about all but one, and use rank of the matrix that I'm looking at as a lower bound on the rank of the tensor, right? So this property is now clearly satisfied. And you can ask, for what rank tensors do I in fact have the equality? Do you see this already?
What's that?
Yeah, clearly, like, if it's an n by n tensor, like of all the dimensions are equal, then I can hope to certify this equality up to rank n, right? Does this make sense? So this is the trivial one. It amounts to, basically matching for rank detection the guarantees of Jennrich's algorithm. Let's say you want to go beyond. So let me give one more example. So this is the trivial flattening. So the second example would make sense not for 3. That's the reason why the case of 3 is very interesting. It will make sense for tensors of order 4 or larger. Okay? So what I'm going to do is, let's say I have a n by n tensor, just for concreteness. Then, I'm going to collapse the first two and the last two modes into a single index and treat this as a matrix. So it's an n by n tensor. It becomes an n square by n square matrix. Okay? And now you can again ask, till what rank can I hope to prove both these properties? And you can see that, it's going to be about n square. Okay? And so, by that reasoning, you can see that n square in some sense is like the trivial benchmark for fourth order n by n tensors. And to overcomplete there, or at least an interesting case there, would be beating n square. But notice that this trick does not work if I have only an n by n tensor. If I contract first two modes and leave the next second one alone, the rank cannot be larger than n. Okay? So, this kind of a flattening often goes by the name of trivial flattening or standard flattening. Does not quite make sense if I have a third order tensor. Okay? Any questions so far? Good, yeah. So, what I want to maybe tell you about is some non-standard or interesting flattenings now. Okay? And our algorithm is going to be based on one such flattening. I'll I think likely be able to give you a complete proof of the rank detection part, and then I'll hand wave the decomposition part away at the end. Okay. So maybe the first interesting flattening in this direction that I can think of is due to Strassen, who gave a map from n by n tensors to 3n by 3n matrices. Okay? And under his map, you can prove that rank 1 tensors map to rank 2 matrices. Okay, so this F, so to speak, is simply 2 times the rank of the matrix. Okay, in this definition over here. So if, so I'm going to say, okay, so rank 1 tensors map to rank 2 matrices. And now imagine taking generic components, R generic components. The maximum rank of M of t, the maximum rank of M of t cannot be more than 3n, right? So you can hope to certify rank of a tensor up to 3n over 2. Does it make sense? And in order for me to certify rank of a tensor until 3 for r less equals 3n over 2, I would want this equality to hold. For this equality to hold, I need generic additivity of rank. So rank in general is sub-additive. But I would like this map to have this generic additivity property in that if I apply, so this is, I should have said this is a linear map. So if I apply to rank 1 matrices, I get a rank 2 matrix. Sorry, rank 1 tensors, I get a rank 2 matrix. If I apply to R generic rank 1 components, rank 1 tensors, and I add them up, I would like the ranks to add. I would like to have no non-trivial cancellations. Okay? This property, of course, cannot hold beyond the dimensions of M of t. So the best thing I can hope for is until 3n over 2. Matching 3n over 2, if I could prove this generic additivity up to 3n over 2, I would indeed get a gadget that works all the way up to 3n over 2, the rank detection gadget. Okay? So it turns out this was done in a PhD thesis of Madalena Persu from 2018. I don't think it appears in a paper, but I think her proof is actually beautiful. So this, she proved that for r less equals 3n over 2, the rank detection actually can be done with Strasson's gadget. So Strasson proposed this gadget, but we did not do an analysis of it until Persu's thesis. Okay.
This is better than Coiran result.
Yeah. So Coiran is not only doing a detection, is also doing a decomposition. Madalena only proved that this works, for detection. She didn't quite, get a decomposition algorithm from there. Yeah. So amongst the things we'll be able to do that. So it turns out that Strasson's gadget can be seen as a special case of a class of flattenings, which, I guess for a while were called Koszul flattenings. But then, we reached out to James Landsberg because he has several papers on it, including the state-of-the-art lower bound for matrix modification using these flattenings. And he told us that it's apparently an instance of a more general class of flattenings due to Young. So we're going to call it the Koszul Young Flattenings. So this is the gadget we're going to use today. So what I'm going to do now is explain this, particular gadget to you. And then, we'll stop, take a break. And then after coming back, I'll analyze this gadget for you. Okay. And it's all the proofs today are going to be super elementary. I'm not going to do anything beyond like basic linear algebra. So everything is elementary. Good. Okay. So I'm going to describe this map. Okay. So M of t is going to be a I'm going to write it like this, but of course, they are the same numbers. So I'm going to take a n by n tensor, and for a parameter p, I'm going to construct a 2p plus 1 choose p times n by 2p plus 1 choose p times n matrix. So it's a square matrix. I'm writing it this way because I'm going to think of rows as p sets and columns as p plus 1 sets. And thinking of it this way also generalizes naturally to the non-square setting. But let's just focus on the square setting for now. So let me maybe give you this explicit map. So you can see, so what I'm going to do is, so look at the tensor n by n by n. I'm actually just going to use the first p slices of the first mode. So first p slices of the tensor. So the first mode, I'm only going to use, indices from 1 through p. I'm going to ignore most of the tensor. Okay, that's all I'm going to use to construct this matrix. So the rows of this matrix are going to be indexed by S comma J for S subset of 2p plus 1 of size exactly p, and J an index in N.
Yeah, so it's the 2p plus 1 first, not the p first.
Say it again?
You take the 2p plus 1 slices.
Sorry, yes, yeah, my bad. Yes, for a parameter p, I'm going to take first 2p plus 1 slices. And then, my rows and columns of m of t, this map, would be indexed by S comma J, where S varies in all possible p sets of 2p plus 1, which you should think of as which subsets of the mode I'm going to use. Okay? And similarly, columns would be U comma K. I'm going to think of them as p plus 1 sets. Of course, you could have thought of them as p sets too, but here it's useful this way. Okay, and now I'll erase this part because this is still the story part, and I want like this definition to be on the board. So say yeah, maybe MP of T here. Okay, good. And so M at S comma J and U comma K would equal okay, so I'm going to explain this definition to you, and then we'll make it act on the rank 1 matrices to see exactly what it does. Okay, so I'm going to describe the entry at S comma J and U comma K. Okay, so the entry only works. The entry only has a non-zero component if S and U have a symmetric difference of exactly 1. Okay, so for a fixed S and U, notice that exactly 1 index would be activated. Everything else is 0. Okay, so basically, if S and U have a symmetric difference, S is a P set, U is a P plus 1 set. You want U to basically be S, disjoint union with some extra index. There can only be one of them. Let's say that is I. Okay, then, I'm going to take the Tijkth entry. So I'm looking at the ith slice. So you can see that S and U together decide which slice to use. Okay, I cannot use more than 1 through 2p plus 1 slices. So I'm using the ith slice now. I'm just going to write down the whole matrix down here, Tijk, right? I'm going to multiply it by a sign sigma ui, where sigma ui is simply -1 to the number of u. So, think of this a natural ordering on 1 through n. And I'm just going to multiply it by -1 to the number of entries less than I in U. Okay?
What is Q?
Oh, sorry, yeah. keep going to the more general version, but yes, let's keep going with q equals 2p plus 1. Yeah. So there is a slightly more general version of it where 2p plus 1 is q. And it turns out that that's the way to formalize it for, non-square tensors. And everything basically succeeds there. But yes, here it's just 2p plus 1. So does the definition make sense? As in, like, you should probably not see why it's nice, but you should at least understand what it means. Okay, good. So before we take a break, I just want to show you what this particular map does to a rank 1 tensor, because you can see it a little bit more concretely there. Okay, and then I'll prove a proposition to you which will kind of demystify why this map is interesting or nice. So let's call this AP of A as the following. So I want to describe to you what happens to a rank 1 tensor A tensor B tensor C. Okay, I'm going to tell you what happens if you compute this map for a rank 1 tensor like this. Okay, so this is an example. So I'm going to call AP of A the following matrix. So it's indexed by, so it's basically a 2p plus 1 choose P cross 2p plus 1 choose P plus 1 matrix. Okay. And you should think of it as like, just taking the first mode of the tensor and doing something with it. Yes.
So I should think of 2p plus 1 equals n, or it's...
No, 2p plus 1. In fact, P would, in the central algorithm, would be a constant.
Okay, so you will only use entries of like I being very tiny.
Correct.
Okay.
I'm just going to use the first 2p plus 1 slices of the tensor.
Okay.
Yeah, absolutely. So, so I'm going to define this matrix APA. So the entry at S comma U so the same over there. So you can think of this as like spreading. So I only have n numbers, a1 through a little n. Okay. In fact, I only have 2p plus 1 numbers here because those are all the numbers I'm seeing. Okay. But I'm writing down a 2p plus 1 choose P by 2p plus 1 choose P plus 1 matrix using it. Okay. And here is some visualization. So this is S, right? I can fix an S, and then there are some S union I kind of elements here, right? So there are like P plus 1 possible choices of this index I that I can take a P set and add to it to create a P plus 1 set. Okay, so there are like P plus 1 indices here, and all of these entries are going to be AI, so on. Okay, so maybe I write it here.
The minus, with a sign.
Oh yes, and there is a sign. Yes, so the sign is important for some cancellation. I'll show you, but for now you can even ignore it. You can see that up to some signs I'm spreading out the entries A1 through A2P plus 1 in this matrix, right?
What are we assuming about the matrix?
So it's a 2p plus 1 choose P by 2p plus 1 choose P plus 1 matrix.
I meant about the tensor that we're now computing.
I'm just telling you how to. Yeah.
It's right.
Yeah. Sorry. Yes.
Where are little b and little c?
Oh, I haven't told you that. I just told you how to take the first mode and create a 2p plus 1 choose P cross 2p plus 1 choose P plus 1 matrix out of it. It's just using this 2p plus 1 numbers, putting them in this particular pattern around to create.
You're going to lead up.
Yes.
Okay.
Yeah.
And then yes, yeah, exactly. M of T is AP of A canonical product with BC transpose. Okay, that's what it is. Okay, so maybe this kind of a maybe this is a little bit more visually easier to see, right? Like it's doing something to A, spreading it out around here, and then, just looking at the matrix of the corresponding slice and taking product. Okay? So, yeah, you should all be kind of somewhat mystified why this can possibly work. I can tell you, so, I don't want to do any proof before we take a break. So I want to tell you just, if you've seen some Kikuchi matrices or whatever in, some context before, this comment would make sense. If not, don't worry about it. You can see that, this is basically a Kikuchi-like gadget, right? Like here the entries, like, the rows and columns are indexed by sets of some, non-trivial index set. And the entries basically are determined by the symmetric difference of rows and columns, okay? I don't want to say anything much more than that, but like, it turns out that it is maybe not an unnatural gadget in the context of these things to use this symmetric difference like objects, okay? If that doesn't make any sense, don't worry about it. I'll come back in 5 minutes and give you a quick proof. So here is the proposition we'll prove right after. I guess maybe I'll prove this. So if I is non-zero, if there exists an I, so fix a vector A. If AI is non-zero, then rank of AP of A exactly equals to P choose P. Okay, so notice that the dimension of the matrix is 2P plus 1 choose P. So in fact, this is going to be a rank deficient matrix, but in an extremely predictable way. Okay, I'll come back and show you that this APA matrix is in fact a matrix of rank 2P choose P. Okay, and this allows you to get what the rank of this Kronecker product is going to be. Like, you know exactly what happens to it because, this is a generic thing, so it's going to be rank 1. So, this entire thing is of rank exactly 2P choose P. And so we can exactly tell you what the rank of this gadget is. And in fact, of course, the kind of structure we, have in it would help us analyze generic additivity too. But, when we prove this, you will see some of the choices I made in the definition. And then, of course, I'll prove generic additivity to you. Good, yeah. So I'll take a break here. We'll come back at 11:41, so 5 minutes.
Somehow when I read the title of your talk,
Yes.
Overcomplete, made me think of more of like the learning theory type of question.
It is maybe I've seen the word get used in learning theory a lot. As in, like, overcomplete often does mean,
More than D samples for a two-dimensional.
I was just talking about tensor decomposition kind of thing.
Oh, learning.
I wonder if complexity theory also uses the same terminology.
Yeah, I was thinking like we have these tensor completion questions.
Yes.
Part of the tensor and
Yes. Yes. There also, I guess, there is a notion of.
There you get more information than you maybe need, right? You can fully complete it if you.
No. I think it's the same.
To the 3 halves.
It's the same notion. No, I think Boaz and Ankur have a paper on it.
You are.
right.
Yes, with that equivalence, yes. With that, so there I think it's the same notion of overcompleteness, like, trying to handle rank bigger than n. Like, can you complete tensors of rank bigger than n? For matrix completion, you clearly need rank, which is
I think it's a difference. You get the number of entries you get when you want to complete it.
That's like roughly n times r. Like that's what you.
N times r. You get more information.
Yes. No, but like overcomplete tensor decomposition, there also I think means that you're trying to complete a tensor whose rank is sufficiently far away from, let's say, like n by n tensor, then the rank is sufficiently far away from n to the 1.5. Yeah. Okay. So I meant that the overcomplete, the word is used in the same sense, in the sense that it is for tensors of rank larger than n. Or is that, or did I misunderstand?
I think the way I understand it is that overcomplete means that you get much more information.
More entries than minimum required.
Yeah, it's not about the end gap.
Okay.
You just get, I mean, n or linear in n would have sufficed.
Well, you need
Maybe the
n times r is necessary just by parameter counting, right?
Exactly.
Yes.
And you need many more. That's overcomplete.
That's definitely true in the tensor case. Yes. Okay.
It's my sense.
Okay.
It's more fitting.
Yes. Yes. Okay. I see what you mean. Yeah. Okay. Good. Yeah. So let me let's just analyze what happens to this gadget for a rank 1 tensor. Right? At least tells us what it is doing, and you will see why the specific signs, etc., appear quite naturally. Okay. So I want to tell you that. So this proposition is saying that if I apply just this operation AP of A, so this 2p plus 1 choose P by 2p plus 1 choose P plus 1 matrix to a fixed vector, as long as the vector has a non-zero coordinate, the rank is going to be exactly 2p choose P. Of course, if it does not have any non-zero coordinate, the rank is clearly 0. Right? So good. So let's, prove this. So, I'll prove it in 2 simple claims. First, I'll claim that, the rank is larger than or equal to 2p choose P. For this, I just need to demonstrate a matrix which has at least that rank. Okay, a submatrix which has that rank. Okay, and this submatrix is going to be easy. I'm going to define it and then draw it for you. So basically, I know that, let's say AI is non-zero. So take this index I and take the set of all sets that don't contain I and set of all U that contain, this is the P plus 1 set, 2p plus 1 choose P plus 1. And this is a P set. So take all rows where the index does not contain a fixed element I, and I is basically the coordinate of A, which is guaranteed to be non-zero. And on the other side, take all U that contain this I. Okay. Now let's see, how this matrix looks. Just a submatrix. Okay. So I have S here. All of them contain, do not contain I. So how many possible S's exist? Clearly 2p choose P. Okay, because one element is fixed and allowed to not be contained, not allowed to be contained. Okay. On the other side, how many do I have? Well, basically the same. Because, all the P plus 1 sets have to contain a fixed element I. So again, 2p choose P. So this is a square submatrix. That's good. Now look at what the entries look like. For every S, there is exactly one U that can have symmetric difference of 1 with S. Okay, namely S union I. Only that entry can actually be non-zero. And so, when it is non-zero, it's going to look like plus minus AI. Every other entry is 0 because the symmetric difference cannot possibly be of size greater than 1. So this is going to be a non-zero diagonal matrix. Clearly, its rank is at least 2p choose P. So I'm done. Okay, makes sense? Okay, so I'm going to prove the other side now. And in order to do this, what I'm going to show you is that every column of this matrix can be written as a linear combination of columns just in this set. Okay, so take the set of all columns where the column index contains I. I, remember, is this element such that AI is, non-zero. There are 2p choose P such columns. I'm going to write every column as a linear combination of columns from this set. Okay. So of course, if the column is in this set, I don't have anything to prove. So let's say, W be a P plus 1 set that does not contain I. Okay, good. So, yeah, maybe I can still continue here, and then I'll draw over there. So let Y be the set obtained by adding back I to W. So Y is a set of size P plus 2 now. Okay. And now I'm going to obtain P plus 1 size sets by removing a different index from W. Okay. So there are P plus 1 different sets I can obtain this way. So let's say Y minus J equals okay. And this is just my definition. Good. So what I want to now prove to you is that these sets are linearly dependent. If I look at the columns corresponding, so if I look at the columns corresponding to all the Y minus J's I can possibly obtain, then I'll prove to you that these are linearly dependent. Okay? Notice that I'm done if I can prove that. Do you see why? So, I'm going to get a linear dependency between, the columns that contain W and some other columns. The other columns are in, this set that I'm keeping. So because it's a linear dependency, I can just write down the column W as a linear combination of columns in this set. That's all. So as long as I can find a linear dependency of W along with these columns, I'm done. Right? Notice these columns all contain I, right? So these are columns in my good set. I just have to write down the column W, in a linear dependency along with this Y minus J's.
Sorry, W is the name of a column now? Or?
Yes, W is a P plus 1 set. So it's an element of.
You're going to find the linear dependency among these other columns, Y minus J's?
Yeah.
So where is W found? Going to express
So this is
W.
just like all the rest of the columns outside of this. I'm also
What am I
trying.
missing?
Wait, sorry, I guess let me make sure I get the notation right.
You want the linear dependence with W.
Right.
All of these Y minus J's and W.
Yes.
Yeah.
W should have an optimal coefficient.
Preferably.
Yes, okay. Let me see. I somehow convinced myself that this is all I need. So let's see. Okay, let me just take a look at my notes because I somehow, I thought that proving that these columns are linearly dependent suffices, but let's see, I'm missing something basic.
Yeah, it is sufficient because if you define J equals I, then you get back to W.
Yeah, but I make sure that my proof allows j equals I.
And if you don't let j equals I, then you are a submatrix.
Correct.
Claim 1, which is
Right. So
linear independent.
So I should allow. So in this proof, I should allow j equals I, basically.
Yeah.
Oh, and that also shows that the coefficient for W is not zero.
Yeah.
Cannot be zero. Yes.
Yeah, because claim 1 shows that.
Correct. Yes. Okay. Good. Yes. So thankfully didn't make a huge error. Okay. So I have to prove that there is a linear dependency in these set of columns. So in fact, I'm going to give you explicit coefficients. Okay. I'm going to choose. So so my coefficients will be of y minus j. My coefficients would be sigma yj aj. Okay. So I'm going to show you that if I take elements of y minus j, the columns, multiply them by sigma yj times aj. Remember, aj is a scalar. Then I'm going to get 0. And I'm going to look at what happens to a single row to prove this to you. Okay. Sorry, all the difficulties are notational. Entry at row S for S. Okay, so now let's compute the entry of this linear combination at row S. Okay. So if S is not a subset of Y, then the entry is clearly 0. Right? So I only need to look at S which are inside Y. So let's say, S is Y minus some 2 elements JK. So S is by the subset of size P plus 2, S has to be a set of size exactly P. So I can obtain it by removing some 2 elements out of Y. Let's say those 2 elements are J and K. Okay. Then notice that the only 2 entries that contribute to this row correct. And there are only 2 possible entries that can contribute. So I wrote down the expression you get by taking those 2 possible entries. And I want to prove this is 0 to you. And this is just like, an exercise in remembering what this entry is. So A S Y minus J. So notice that A S Y minus J actually equals sigma of Y minus J times AK, and A S Y minus K equals sigma of Y minus K J. Okay, so I just literally wrote down what the AS. So remember, the symmetric difference of Y minus J and S is exactly the element K. The symmetric difference of Y minus K and S is exactly the element J. Right? So I wrote down exactly what the entries are according to this rule over here. Okay, so now notice that AS Y minus J has a term AK, so AJ and AK multiply. Same with over here. So the only thing to check is that the signs multiplying them are of opposite nature, right? So why is that going to be true?
One appears before the other.
Correct, right? So J, let's say J appears before K. Then notice that I think the signs of these 2 are flipped. Yeah, I think well. It works out. Yeah. Basically, you just need to use that J is before K and then notice that, one of them is counting, like when you're counting these parities, one set has one less element, and that's it, right? Like so. So that's pretty much it, right? It's very explicit, very concrete proof that you're going to get a linear dependency. And because this is true for every row, and the rows I'm including include W, I found a linear dependency of W along with the columns in this set over here, right? And so, and the coefficient of W must be non-zero because otherwise, it violates claim 1. So I can rearrange and basically write down the column W in terms of the others.
It's the same proof as the determinant of a square matrix with two equal rows or columns, let's say, is 0.
Yes, the sign, yes.
Expanding.
Yes. And the sign there appears for the very similar reason. Good, yes. Okay, so you at least see, so the notation is kind of confusing, but I hope you see that the proof is completely elementary and, very, very easy, okay? At least a single board proof. Okay, so what I want to do next is prove, sorry, what?
Explain why you would define this kind of.
It's like this guy, if you think exterior algebra, these are word products of these vectors, and you know what they are. I mean, it's just explicit calculation. But
Which product of the first P?
You see that in the exterior algebra defined by these columns, the rank is 2p to p.
Is there a simple way to?
No, I don't. I mind. Gil tried to explain to me.
Yes.
And he lives there, and then you see everything.
Which product isn't it like tensor product when you mod out the order?
No, you add sign.
Yeah.
You add sign.
We don't have here a product of P different.
No, it's not a normal product. It's a west product. Doesn't it? Yeah, I don't. I mean, if I could explain it, I would. But it's very natural.
I should say that,
It's not like some people thought, oh, what a clever way to get cancellation. It comes out.
I'm not so much worried about the cancellations as what are these P sets doing for you? Are they allowing you? Yeah.
The P sets are written algebra which contains products of P out of this. It's a way to multiply tensors like tensor product, but with a sign. So the determinant of n vectors is simply the weight product of this n form.
It does seem to me that understanding this algebraic reason would be nice for me to understand this own proof. But yeah, the argument we have is basically, you can think of it as a brute force argument. Everything is linear algebra. We did not use any of the meanings of these objects that they come from because frankly, we could not understand them well enough to use them. So all of our arguments look basically explicit like this. But what Avi is saying is that there is probably a way to do this.
Certainly a way to do it, and the definition is very natural.
Yeah, no, this proof you can definitely do.
No, but I'm saying the definition of
yes.
it, yeah.
Yes. What I don't know is a proof of generic additivity. So Landsberg, for example, when he considered this definition, he did prove that in the undercomplete regime, there is generic additivity for this flattening. So he did.
Meaning that if you take two tensors.
Yeah, so if you take up to n generic component rank 1 tensors and add them up and apply this flattening, then the rank does indeed become, the rank is exactly additive. But he knows how to.
In the world of the flattening.
In the world of the flattening, in the matrix rank world.
Yeah.
Right, so the rank of this flattening is additive up to generic rank n tensors, little n tensors.
Meaning that the sum would have generic rank 2n?
Yeah.
Yes, or 2p choose p times n.
Yeah. For p equals 1, you get 2n. Certain p equals 1.
So, right, like for oops.
But if you choose larger p.
Then you get 2p choose p.
Yeah.
Okay.
So he knows how to prove this generic additivity until up to rank little n. And what I'm going to prove to you that in fact the generic additivity holds till by basically some function of p that if you make large becomes 2 minus epsilon n. That's the thing I'm going to prove to you now. Yeah, does that make sense?
Yeah.
And
Okay, cool.
that's the limit?
Sorry, what?
And that's the limit?
That's the limit, yes. Certainly for this, yeah, certainly for this one. For linear flattenings, you can go until, in principle, 6n, like other linear maps. This is a specific linear map from tensors to matrices. For other linear maps, you could potentially do better, but not beyond 6n. And it turns out that if you in fact consider in an appropriate way degree D maps, then there is some f of d times n that you can reach. But in particular, for constant degree, you can't beat order n.
Okay. But then it won't be like additivity, right? It will be some degree D combination.
You can still think of it as additivity in the sense that, I defined this rank detection gathering in the previous part of the talk, right? So I would like this f to somehow give me the tensor rank for the matrix rank. And I would want this f of, rank of m of t to be equal to the rank of t. That's what I would call additivity there. I mean, it's a funky definition, but it's what I would call additivity.
You said f is degree D. It's not.
No, f is not degree D. The map
E
to m of t is degree.
Oh, okay.
Yeah, but in some appropriate restricted way that maybe let's not consider right now.
I see.
Yeah. But there is some generalization of this kind of flattenings you can define, and you can at least prove that they won't allow you to significantly better these results. But yeah, for all we know, there is like a crazy nonlinear map that can do much better. We don't know. Okay, so I'm going to erase this argument because I want to keep this board around. But maybe let this proposition be around. Okay. Okay, so I want to now prove to you, write down the concrete parameters. Yeah, so we'll just work with, yeah, maybe I'll just write in short that if P has R n by n by n generic components, then generic additivity holds for R at most 2 times n times 1 minus so you can completely ignore these terms. You should think of it as like if P becomes large enough, then I can make this 2 times n times 1 minus epsilon for large enough n. Okay, so do we understand the theorem here? Okay, the statement, yeah. Okay, good. So let's maybe move it here because a bit more space. Okay, so like I said, the proof is just basically explicit linear algebra. So I'll at least try to show you all the steps, even if, the notation is a little bit annoying. Okay, so, let's assume, so, for any A, if we know that AI is, maybe I can write this part here because you want to remember it. So if AI is non-zero from this proposition, then the matrix AP of A can be factored as a diagonal matrix times A tilde times a diagonal matrix. Let me explicitly write down what this matrix is, and you'll see why it's kind of natural. So V sub S has the entries product of inverses of AI in S, and W sub U is the product okay. So here's what I'm doing, okay? So look at this APA matrix we defined over here, okay? It depends on this vector A, right? But notice that, what I can do is I can try to pull out all the dependence on A and think of multiplying the matrix with some diagonal matrices on rows and on left and right. And in the middle, I'll basically have this matrix for the vector 1, the vector of all ones. Okay, that's what I'm doing. Okay, so notice what I'm doing here. I'm writing APA as diagonal matrix V on the left, diagonal matrix W on the right. The entries of V sub S is basically the product of inverses of AIs, where I is in S. And similarly, on the right, I have product of AIs, where I is in U. Notice that if I multiply out AS, like VS with WU, where S and U have a symmetric difference of a single entry, and U is a larger one, then I get exactly AI. Okay? So you can see that, this is like, there's a natural factorization where tilde A is basically this matrix for the vector of all ones. And I factored out the dependence on A in terms of this vectors V's and W's.
That's very nice because that kind of relates to the wedge product description.
It does?
Because it has these products, PYs or P plus 1 mod Y's products.
Ah, sure,
So
yes.
it's like behaving like a P-tensor in some sense.
Yes. Yes, that is the inclusion. Yes. That, so we have, it's a formal 2p plus 1 degree polynomial that happens to, have cancellations and be linear. That's how we are doing it. Yeah, which is what I also view Kikuchi as doing, but okay. Yes, but anyway, yes. Yeah, that's the factorization. Good. So because, A tilde is this transformation for the all ones vector, and all ones vector has no non-zero coordinates, this proposition applies, and the rank of this matrix inside is exactly 2p choose p. Okay? And notice that, you should have worried a little bit that I'm writing down product of inverses, but A is, because A is generic, all these numbers are, reasonable. There is no zero in the entries of A. Okay, makes sense? Good. So, A tilde is formally 2p plus 1 choose p by 2p plus 1 choose p matrix, but its rank is only 2p choose p. So I want to factorize A tilde with so that the inner dimension is exactly equal to its rank. Okay. So I'm going to write A tilde as Q tilde R tilde transposed. Okay, where Q tilde is exactly what you think it should be. As in, like, its dimensions are exactly what you think it should be. 2p plus 1 choose p cross 2p choose p, and same for this guy. Okay, good. So now, if I look at this representation of AP of A and like plug in the factorization of A tilde, then I can write, this is the final thing I'll use, AP of A as QR transposed, where Q is basically diag V times Q tilde, and R is diag W times R tilde. Okay, makes sense? Okay, good. So, I can write down the matrix M of the tensor now by basically just, taking this APAs, taking canonical products with like the corresponding B's and C's and adding them up. Okay. So M is okay. So I'm going to call this matrix AP of A applied to A to the L as AL. And this is basically that particular factorization applied to the Lth component AL. And then I'm taking like, the canonical product with BLs and CLs. Okay. I'm going to write down this explicitly in terms of what we computed over there.
So what is BL and what is CL?
So I have a tensor. So I'm applying the map M to the tensor AL, tensor BL, tensor CL. So L at the top means Lth component. Okay. So I have Q1 up to QR, but I'm taking canonical products with B1 up to B sub R. And then on the other side, similar but with C's.
But maybe you want to make this not look like it's well matrix, right?
It looks rectangular, no?
So the other one should be rectangular. Yeah, okay.
Sorry, yes. Yeah, so I just, explicitly took the canonical product and that's how it looks like. Make sense? Okay, so
Well, you did show us the decomposition to pure right?
Oh, that's all I'm going to use.
But did you show us how it?
You mean an explicit computation of what Q tilde looks like? No, I'm not going to use that. Yeah. I just want to use the factorization because then I can club Q's with B's and R's with C's. That's all I want to use.
It doesn't exist by the
Yes.
Yeah.
Yes. Yeah. That's all I actually am going to use. Okay. So now let's say that the rank. So like find the smallest integer M, positive integer M, so that R is at most MQ. So it need not be equal to MQ, but in some sense you can always add some more components if you want, and assume R equals MQ. So this is in some sense the interesting case. So we're going to assume that there is some integer M such that R is M times Q. Make sense?
Q is 2p.
Q is 2p plus 1. Yeah, maybe it's easier for me to. Yes. So, these numbers are going to be a fixed constant eventually. So, I just want the rank to be a multiple of this constant. You can see that it can't possibly cause the error. That's, by the way, the cause of this minus 2p plus 1 over here. Okay, so, good. Yeah. So, what do we want to prove now? So, I have a factorization. I would like to prove that this is basically a full rank factorization. Right? Like basically I want to show that, its rank is as large as it possibly could be. So how large can it possibly be? Each of these Qs has inner dimension 2p choose p. Right? And there are R, so this is a width 2p choose p matrix, and I have R such column blocks. So the maximum possible rank of this block can be R times 2p choose p. Okay, and I'm going to argue, or actually sketch to you that that's exactly what it is. Okay, good. So, good. So what I'm now going to do is look at the so I'm going to analyze the two factors separately. Look at, the first factor. And now, I'm taking a canonical product with this vector B, right? So I'm going to get copies of Q1 multiplied by each possible entry of B's, right? I'm just going to write down it as a block matrix where Q1, QR, etc. appear as blocks, and they get coefficients which are entries of B. Okay? So I'm going to write it as B11. So B11, the right rotation would have been one at the top and one here, but this is maybe a little bit easier to write or faster to write. So this is Q1, so on up to, okay, and then I have B12, Q2. So now what I'm going to do is so I have M times Q blocks here, right? And how many blocks do I have over here? So this dimension is 2p plus 1 choose p.
Yeah.
Times n, right? So I'm going to write this as a collection of m by m blocks, little m by little m blocks. Okay. So over here I have R times 2p choose p columns. Okay, so R is M times Q. So I'm going to break them up into Q times 2p choose 2 different blocks of size M each. Okay, so I have okay, so I have Q blocks written over here. Okay. And what I'm going to do, so I'm going to 1, so on up to B, Q minus P, 1, Q1. So same over here, B2, 2, 2. So what I'm doing is I'm dividing this matrix into M by M blocks, and I'm writing down it as like a collection of M by M grids. Okay. And the key point is that, I have these coefficients B's that are multiplying, this Q1, Q2, etc. Okay. Remember, these Q's depend on A, but they don't depend on B. Okay. Like the way we have constructed. Okay. So let me be a little bit sketchy at this point now. Once you have this block structure, okay, I want to prove to you that generically, it is full rank. Okay. For this purpose, it is okay to restrict to just diagonal blocks. Why? Because I have pulled out the dependence on these B's. The B's are generic. Okay. So I can set some of the B's to 0 and analyze it for just the remaining B's. And if I can prove that I am full rank even after doing that, then I'm only doing better. Right? Said in a different way, I want to analyze the determinant of this matrix. I just want to prove it's non-zero as a polynomial. It's okay to prove this if I can set some of the variables to 0 and then argue it. Okay. So the problem reduces to just analyzing diagonal blocks. Okay. And then, the diagonal blocks, what I'm going to do, I won't write it down now. But for the diagonal blocks, what I'm going to do is I'm simply going to compute the determinant as a polynomial in the B and A entries. And in some sense, there is only one thing I can argue now. I have to argue that there is some coefficient which will, never vanish. Okay. So there is more dungeonness just like this, but because I'm going to use the last 10 minutes to tell you a little bit more about the problems, maybe I won't do the entire argument from here on in detail. But basically, the idea is that I'm going to restrict to the diagonal blocks. Then for each diagonal block, I'm going to take, so then I can argue about each of the blocks, separately. I'm going to take the determinants of each block, think of it as a polynomial in B's and A inverses. I need to think of A inverses for the left factor and A is in the right factor. and then use genericity to, basically argue that some coefficient would be non-zero. Yes.
So why you have two indices for B? Isn't B just a vector?
Yeah. So, there are possible vectors.
Yes.
There are possible B's. So B11 really means B11. This was just.
Okay, that's.
Sorry, I was being lazy. Yes. Okay. So yeah, I mean, it's a very explicit proof. It's a very, linear algebraic proof. And maybe like Avi from earlier had a comment like, maybe we should try to figure out if this proof has some algebraic meaning, because that might allow us to understand it better, or at least do it in a less grungy way. But right now our proof is basically just write down the explicit matrix and then muck around to prove that it is, it has the rank that you think it does. Okay. One thing I want to mention before I say other question. So this one, this argument gives a rank detection, but it doesn't give you a decomposition algorithm. So I won't tell you the entire algorithm, but I want to point out a very nice primitive that's very useful, and it's due to Johnston, Lovitz, and Vijay Raghavan. It's actually also recent work from maybe 2023, maybe like less than a year before, when we started thinking about this question. Here is the very nice primitive that they give. Suppose you have a subspace pi of matrices. Let's write down the square case, it works in the rectangular case too. So let's say you have a subspace of n by n matrices. And suppose, it was constructed as a span of S generic rank 1 matrices. And whatever is the remaining thing, let's say arbitrary. Okay. The only thing required is that these rank 1 components and these matrices should be generic. One concrete thing you can keep in mind is start from any rank 1 matrices and any collection of matrices, that many of them, and add like a tiny random perturbation. That's some concrete model you can keep in mind. So the span of this would be what I'm going to call a generic subspace. Okay. Then, it is not so hard to prove this. Yeah.
The dimension pi minus S is.
So, so think of the case when S equals dimension pi first. Okay. Then I'm just saying that, choose some S or dimension many rank 1 matrices that are generic and take their span. Now, what I'm allowing is that this subspace does have some basis, like in the fixed basis I'm choosing, some basis elements need not be rank 1. That's this arbitrary part. Right? Just basically choose some remaining matrices which are arbitrary, just choose them generically so that they don't have any kind of fixed polynomial dependence on the previous one, for example. And S, are like, so all of these components are generic. And take their span. Then it turns out this part is not difficult to prove. In fact, it was known in algebraic geometry that the rank 1 matrices that I use to generate the subspace, in fact, are the only rank 1 matrix in this subspace. Okay? Like you need S to be sufficiently small compared to n square, but this is true if S is sufficiently small constant times n square. What these people do is they give an efficient algorithm to actually calculate this S rank 1 elements.
So the genericity is essential. It can be hard to.
Correct. Yes. So I do want to mention this point that Avi is mentioning. It turns out that if I give you a subspace which is guaranteed to have a rank 1, a subspace of n by n matrices, it's guaranteed to have a rank 1 matrix inside of it, finding this rank 1 matrix or even approximating it is a hard problem. The best algorithm we know is actually some old paper that I wrote together with Boas and Streuder. There is, in fact, a 2 to the root n algorithm for solving the worst case question, in the sense that I can find 1 minus epsilon projection rank 1 matrix in the subspace with this algorithm. What they show is that if you have genericity, you can do this in polynomial time. Okay, so this is a super cool primitive. And what we do is we show that by basically just mucking around a little bit more with our rank detection, we can reduce, or we can basically find an explicit subspace where the components A's and B's form the rank 1 matrices, in the basis. So basically, we can then reduce to this particular primitive and recover the rank 1 matrices, which actually give us the vectors we are after. Okay, so this primitive is actually super useful. Now, in the last 5 minutes, I want to end with a sequence of open questions, because I think there's a lot that we don't understand here. First, everything I told you, you could have asked, what's the model of computation I'm talking about? Like, how are real numbers represented and such? So if all the inputs are rational, which is maybe the way to think about this question meaningfully on a computer, then the algorithm I give you runs as long as you can compute things up to polynomially many bit precisions. Right? I'm only going to do basically in algebra, so like inversion of a matrix, computing eigenvalues and such. So I can, as long as I can compute poly and bits of precision, I'm good. But this is bad in the sense that if instead of the tensor, like we saw in today's talk, I gave you some perturbation of it, like t plus a small noise, then all these algorithms break unless the noise is exponentially small. So these algorithms, including like coherence algorithm, all those algebraic algorithms in general, they do have this issue that they are extremely brittle.
Again, so if you apply the smoothing to your input.
No, it's not smoothing. Okay. So like so smoothing is like being applied to the components. So the rank of the tensor doesn't change. But now imagine that I give you the tensor T plus some, let's say, a random Gaussian mate like tensor. So this is perturbing the whole tensor, right? So, you're getting the Gaussian tensor that I'm adding could be very small, could be like inverse polynomially small, but it is still a non-trivial noise. All these algorithms will break if I give you this noisy version. They can tolerate only an exponentially small amount of noise. They cannot tolerate inverse polynomial noise in the scale of the problem. And this might look like an academic issue, but it's not. Most of the reductions I told you earlier in statistical estimation, they require that this primitive be present because we're always computing this tensor we are after from samples. So there's going to be a sampling error. And if you have polynomially many samples, you should expect inverse polynomial kind of error. So we are in trouble if we cannot tolerate inverse polynomial noise. And so it turns out that we still don't know such an algorithm. And it relates to the issues of understanding the singular values of perturbed matrices, and turns out the lowest singular value is a harder question to understand. So that's like the main issue here. So I'll say robust algorithms is an open question. And in particular, you could ask, is there a robust version of this JLV primitive? We don't know so far. So that's the most immediate question. But I want to maybe write one more because that's, I think, very nice, and maybe say a few sentences about it. So this goes back to Kevin's question from earlier. Oh, sorry.
I want to ask about this JLV.
Yes.
So what is the input?
The input is this, some basis for pi. It may not be this basis.
Okay, and for what S? Their algorithm is efficient?
So the dimension of pi, S doesn't matter. S can be as large as dimension of pi. The dimension of the subspace I'm giving you needs to be tiny enough constant times n squared.
Okay, and wait, S doesn't matter?
So all I'm saying, so S.
The bigger the better.
Exactly. The bigger is only helpful to you in some sense because, then the subspace is even more kind of spanned by just rank 1 components.
Okay, but let's say S equals 1, then you are just finding one rank 1 in the subspace. And their algorithm also work in that way.
Yes.
Okay.
As long as the dimension of pi is, at most some small constant times n squared. And notice that, there are assumptions, right? Like the rest of the component needs to be generic.
Yes.
You can't tailor them to this rank 1 matrix. But yes, up to that, their algorithm will work.
What's the robust? Can you kind of spell out the robust version that fails?
Yes. So, instead of pi, imagine that I give you, a subspace which is obtained by, let's say I take some basis for pi and I perturb each basis element by adding some little bit of Gaussian noise and then take the span. You can even take, add Gaussian noise to these particular basis elements. Now, it is still true, like if you add sufficiently small noise that, there will only be these components which are,
Close.
yeah, exactly. So it's still a legitimate question, but we don't know how to do that. In fact, come to think of it, we also don't know in the worst case. It turns out that, doing that would have complexity consequences in quantum, which is the reason why we were caring about this. The generic case doesn't really do anything for quantum, but, still, interesting question. Yes?
Just a quick question. Does the JLV and maybe another, like the theorem that you mentioned, work for symmetric tensors as well?
Yeah, very good question. No.
Yeah.
So the genericity required right now is really, so, it's in some sense, the genericity is a non-trivial requirement in terms of how it plays with symmetry, right? Like if I allow A, B, and C to be equal, that's like a non-trivial constraint, non-trivial relation. And that does break, both our algorithm and JLV. Yes.
Oh, so the JLV also doesn't work.
Yes. Yeah. So it is an asymmetric rank one problem. Yes. Yeah. Good question.
Do you conjecture that this can be extended?
I would say so, right? Like right now, I mean, the difficulty is that there is some complicated matrix which we have to understand the singularity of. And if you force me to deal with one more relation, then, my life gets complicated. But it's still probably true. Yeah. I don't know. Yeah. Okay. So let me just mention one more and then I'll stop. Okay. So this goes back to Kevin's question from earlier, which was like, is certification or rank detection necessary for decomposition? And in principle, not. You could decompose tensors without like certifying that the decomposition you're producing is min rank. So let me produce a concrete question for you. Okay. Let's say AI, EI, CI are arbitrary vectors, and are many vectors, are many triples of vectors, and I give you AI tilde, BI tilde. So I'm gonna take the tensor with these components. Okay, so I'm giving you a tensor with rank R, obtained by starting with arbitrary vectors. And then tilde means that, I just added Gaussian or independent Gaussian vector to AI. So this one is just AI plus a Gaussian. And this is independent in every coordinate. So it's like a smoothing of the original input. And the question I'm going to ask is, can you decompose this in the overcomplete regime? Beyond some constant times n. And in order to tell you that, this is not a crazy question, let me mention a result. If the smoothing is large enough, like if the smoothing becomes large enough, then, you can think of the components themselves as just random vectors. So think of this as the limiting case. When AI, BI, CIs are just independent Gaussians, that's like, the limit of the smoothing. So if AI tildes, or like AI, BI, CIs equivalently, are random, then we in fact know algorithms that work all the way up to n to the 1.5 over polylog n. So this is a result due to Peng-Yu Ma, Jonathan Shi, and David Streuler. So for random components, we in fact not only can handle C times n, but we can actually go all the way to under 1.5 up to some polylog n. Of course, they're not certifying rank here. If they could, that would be a very interesting result, but we can't do that. We don't expect to do that. But they are still able to find the components if I gave you the model of their generation. So there's a subtle difference between them that I can find these components uniquely, even though I'm not quite certifying that this is the only min rank decomposition that the tensor has. Okay?
You're not certifying that it's min rank at all.
Correct. Yes.
It may be bigger than what you need.
Yes. Yeah, so I'm not certifying that it's min rank at all, but I can still guarantee you that I'm finding these AIs, BIs, CIs. So I am finding the unique components that were guaranteed to exist by my generation process. So for the random case, we know this. If I make this noise smaller, then, these results disappear. We don't know any result. In fact, right now, for inverse polynomial, in fact, like anything which is tinier than a constant noise, where like, for example, this trick stops working, we don't have any algorithm beyond what I told you today. So 2N, basically. Even though this problem should be, in principle, much simpler than certifying tensor rank. So yeah, a concrete open question is, if I give you a tensor made up of smooth rank 1 components, much bigger than constant times n many of them, can you find these AI, BIs, and CIs? Yeah, without, of course, certifying tensor rank. If you can, that's even better. You can hope to do it without. Yes. Yeah, that's all. That's all I'll say. Yes.
Okay, we have plenty of questions, but you have a question?
I have two questions.
Yes.
The first one is why your analysis only stop at like 2 plus epsilon?
2 minus epsilon?
Is there an intuition for that?
Well, I mean, the intuition is that, this particular gadget doesn't make sense, right? So look at like the gap between 2p choose p and 2p plus 1 choose p. Right? Like I'm already like, factor 2p plus 1 off. Okay, let me say it this way. This particular, there is a very easy way to see why this particular gadget cannot allow you to do better than 2.
Okay.
You can, and yeah, it's simply like, just looking at the definition a little bit, nothing more maybe beyond that. But it turns out that, even things of this type, like, this symmetric difference structure, etc., you can show that even those won't allow you to go beyond 2n. This particular gadget doesn't work is maybe relatively easy to see, yes.
So you were saying like like that comes from 2p plus 1 choose p versus 2p choose p?
Yes.
But why is that?
So maybe yeah, okay. So I mean, short of showing you the proof, I don't know exactly how to explain it very clearly, but basically, like, you can find like some kind of a trivial dependency that starts arising if you have too large a rank.
Okay.
Right? Like, and it's just like the structure of this matrix that forces this dependency. So seeing that this breaks down at 2 is maybe relatively easy.
Okay.
Yeah.
A second question is, any of this thing work in finite field?
That's a good question. So Koiran's algorithm works on all large enough fields. So the other, like the 4n/3 result I mentioned, actually does work on every large enough field.
Like large enough meaning how large?
Polynomially large, yeah.
Okay, like constant size won't work.
No.
Constant seems, yeah.
Okay.
You'll have some weird relations and then you'll be in trouble, yeah.
Okay.
But yeah, large enough polynomial compared to the number of parameters you have, should basically work. Our algorithm, probably there is a version of it that could work in finite field, but we never thought about it. So like, the way I described it only works over complexes or reals. Right, like, there are many subroutines, for example, you have to upgrade to finite field version. For example, J and V, I don't quite know. Yeah, anyway, yeah.
A conjectural answer to the first question. I think it has to do with the gap between commutative rank and non-commutative rank of symbolic.
Oh.
So I'm really wondering if there's an analog of your algorithm for the symbolic case, like the vectors A, B, and C are made of variables, but you need to scramble them with linear combination with random variables.
Yeah, that's a good question.
And then also,
and then you can ask, like, what if I label them with matrices instead of scalars?
No, symbolic. No, I don't want to.
Oh, okay.
And
but what's
the gap between? Yeah, I think the construction here of these flattenings is very related to generating the largest possible gap between commutative and non-commutative rank.
Okay.
And you cannot make it bigger than 2, and or 2 minus epsilon is the same construction.
Okay, yeah, I mean, I think it would be good. So where would the linearity of this, I mean, presumably for nonlinear maps, you should be able to go beyond, or maybe you can go beyond. So where would that show up in this commutative, non-commutative rank distinction?
With the linearity.
Yeah. Like, this particular map was really about.
I mean, all the arguments which you presented and in many other such, you argue about rank 1 and then you use subadditivity of rank 2 to ensure your first property of the rank certificate.
I see. So it probably would apply to linear maps.
Any rank method,
Yeah. Linear map with like rank of the matrix at the end. Yeah.
More questions? Okay, thanks so much.